Python's match operator offers incredible flexibility here. We start with a basic variable, day of the week. Next, we'll use the pipe operator to evaluate multiple conditions at once, specifically checking for Saturday or Sunday. Think of the pipe symbol as a logical OR, a classic pattern in modern coding. From there, we can still handle standalone cases. For instance, isolating Monday to trigger a specific action. Finally, the underscore serves as our wildcard to catch everything else, no matter what the user inputs. This final underscore statement will seamlessly catch it. It's a perfect safety net. Let's run this code and watch weekend mode instantly activate. Since the input is Saturday, it hits our very first condition, matching Saturday or Sunday, a flawless match. Now, if we switch to Monday and execute the program once again, you'll see weekly planning kickoff right away. What about other days? The underscore handles them. Let's swap it to Tuesday and hit run. Just like that, it triggers a regular work day. But the underscore is capable of much more advanced behavior. We can introduce a powerful guard condition right here. This allows you to customize structural matching with traditional conditional logic. While this is a straightforward example, it scales beautifully to complex scenarios. Here, we are actively validating if the day is exactly equal to Saturday or Sunday. Notice how cleanly the wildcard underscore behaves with this setup. Instead of a generic fallback, we unlock precision control by implementing a dedicated conditional guard. Now, both elements must align. The case expression catches the match, while the guard ensures the criteria is met. It must evaluate to Saturday or Sunday. When a simple pipe operator isn't enough for nested logic, and you require strict conditional oversight, this guard syntax is an excellent approach. It achieves the exact same outcome with maximum readability. As expected, weekend mode is successfully activated, but watch what happens if we change the input to Tuesday. It immediately defaults to our regular workday condition, clean and highly predictable. Both approaches help clarify how the wildcard underscore operates. By appending a guard statement, you introduce a powerful layer of validation, ensuring that specific criteria are checked dynamically on the fly. Mastering Python's match operator with if statements is simple. Imagine a scenario where your variable holds a temperature of 32. Hot. Let's design a dynamic system to display weather alerts for our website visitors. We specify if the temperature is 40 or higher, trigger an extreme heat warning. But remember, this isn't about weather. It's about the guard. Here, we initialize a temporary variable. This variable instantly captures the incoming data value. Data. The moment it arrives, it binds to this variable, allowing you to run conditional checks straight against it. In this match block, our named capture variable handles the logic perfectly. If temperature is 40 or more, we execute an extreme heat alert. Next, we check if it's 30 or higher. Python evaluates these conditions from top to bottom, meaning your pattern cases must be mutually exclusive. If you place a broader condition first, it shadows everything, and subsequent blocks will never trigger. Order is vital. Always track how this capture variable behaves. Now, let's unlock an even cleaner approach. We can leverage chaining to validate specific ranges. Look closely at match temperature again. See our capture variable? We apply the conditional guard right here. This evaluates if the value is between 20 and 30, a comfortable range. How do we read this? Chained logic can seem confusing initially. Let's break it down mathematically. Is 20 less than or equal to 19? 19 is our input. So, is 20 less than or equal to 19? Clearly it is not. This means the expression equals false. Testing if 20 is under 19 immediately returns false. It fails. Next, is 19 less than or equal to 30? Yes, true. One part is false, so the guard blocks it. Executing this confirms it falls outside our comfort zone. However, here is a brilliant trick to read chained logic. Is the temperature 20 or higher? Flip the perspective. Instead of is 20 under 19, ask if 19 is greater than or equal to 20. They mean the same thing. Reading strict math notation can feel clunky at first glance. False. But checking if 19 is 20 or above makes it instantly clear why it fails. The absolute syntax reads 20 less than 19, which sounds counterintuitive. Simply shift your mental framing. Is the temperature greater than or equal to 20? Invert the operator direction as you scan it. Keep the code exact, but read it with ease. Note, write it standard, read it fluidly. Next, is the temperature 30 or under? It matches here, but the previous check blocked it. Let's switch our testing value to 22. Perfect. Now we land safely within our comfort range. Want to know what this syntax does? You're looking at a powerful Python feature that many developers miss. The match statement arrived in Python 3.10, and it's a total game changer. Imagine handling a tuple containing multiple elements. Let's take a specific employee, storing their name and their job title. Our goal is to use structural pattern matching to instantly check if this employee is a manager. This kind of complex conditional logic can be incredibly messy in other languages, but Python makes it effortless. We start by matching against the employee data. Python evaluates the input, extracting the structure directly. The data comes through cleanly as a tuple. It contains literal values, like the name Samantha, paired with a job title like manager. Each case statement beautifully deconstructs that tuple. The name variable captures the first element, which targets Samantha in our example. Meanwhile, the second item acts as a specific condition. We check for exact matches, like developer, manager, or designer. Notice the final underscore block at the bottom. That serves as the catch-all fallback for our match statement. Think of the underscore as your ultimate else clause. It triggers when nothing else matches. With the name variable mapped across these cases, the incoming tuple passes directly into the evaluator. See how it works? The data flows effortlessly, right where it belongs. As the pattern unpacks seamlessly, the employee's name binds to the variable, while the second part verifies if they are the manager. When it detects a match, that specific block instantly fires. Let's run it and watch the perfect output appear. Samantha leads the team, exactly as expected. Let's change her role to developer. Boom, the output dynamically shifts. Samantha writes code. It scales effortlessly without altering your core logic. You can track roles, status updates, or complex states with ease. That's the pure power of Python's match. Did you know Python can do this? Look at this dictionary. We want to match its pattern instantly using the match statement in Python. This functions like a switch case block in other languages. Think of case when in SQL or select case statements elsewhere. Essentially, we are tracking a specific type of event here, an SMS, with T-Mobile as our provider. Running this code returns an unknown event. The system checks every statement line by line, fails to find a match, and hits the fallback. Why does this happen? Because the case block itself mirrors a dictionary structure. We look for a type. See, it must be SMS, which aligns, but the provider requires Vodafone. That does not match our incoming dictionary data. But watch what happens if we change the provider to Vodafone. Let's run it. Boom. It triggers sending SMS message. Now let's switch our input service type over to email. We can remove the provider for now, or leave it in to show its power. Let's keep it. Notice what we have here. The type is email. Right. This case statement checks both fields, the provider and the type. The next block only filters by type. Executing this gives us sending email notification. Why? Because the pattern is simple. It just checks. If the incoming dictionary is an email type, it completely ignores the provider. But what if we enforce a strict provider requirement? Like requiring Gmail? Suddenly, this case will no longer match. We get unknown event. Let's change the provider to Gmail. Perfect. Now we have an email type paired with Gmail. Run it, and look at that. Sending email notification. It works seamlessly with both properties, both the type and the provider. See how incredibly useful dictionaries are here. Using the match statement makes this so clean, where other languages would really struggle. The syntax is remarkably simple. You just pass the structure of the data you want to handle. And you can pick and choose. Tell it to ignore the provider if you want a broad match. If that's the only target, it works perfectly, regardless of the provider. Or you can expand it and capture the provider, or any key value pairs you want. Hopefully, you learned a fantastic new trick that you didn't know before. If you did, please follow, like, and subscribe. It helps the channel immensely. See you next time. Ever wonder what this statement does? Mastering if statements as guards within your match blocks is an absolute game changer. Take a look at this match statement. It elegantly checks whether our target day exists inside this specific list. Let's run the code. Boom, we instantly get weekend during summer. That's because our day is set to Saturday, triggering this exact condition. Next, we want to layer in a brand new variable, the season. We need to verify if it is currently summer. Only then should this output trigger. Executing this gives us weekend during summer perfectly thanks to this powerful addition right here, known as a guard statement. Check this out. We pair our baseline match condition with a guard expression. This if clause acts as a gatekeeper. Once matched, it checks this extra rule. It ensures that the season strictly equals summer. Watch what happens when we switch the season variable to winter. This first print block should no longer execute. Running the script confirms it. We get no special match. Let's add a brand new case to handle other seasons easily. We'll duplicate the case and update the guard to look for winter. With winter set, we'll print out weekend during winter. Let's run it, and there it is, weekend during winter. Caution: string matching is strictly case sensitive in Python. Capitalizing the word will break the match completely. Notice how an uppercase letter throws a no special match result. Reverting it to lowercase aligns it perfectly with our condition, bringing back our correct output instantly. That is the true power of a guard statement. The match case block will only execute the given rule if the guard is also true. You can scale this technique up for any scenario. See this advanced variation. You can chain multiple conditions right inside the guard, like checking the season and year simultaneously. You can evaluate multiple criteria at once, or you can use a wildcard underscore here. Even while tracking season, year, and day, this underscore acts like a catch-all else statement. It triggers automatically for every single match, letting the guard statement handle precise filtering. Boom. Python gives you incredible flexibility with conditional logic. The choice of pattern is up to you. Keep it clean and straightforward by letting the guard handle specific triggers, or leverage the wildcard underscore to put guards front and center. Adding these clean techniques to your Python toolkit will make your code sharper and more efficient. Keep exploring, and I'll see you in the next lesson. Let's dive into Python iterators. An iterator is a powerful object that processes values one by one. Take a look at this list. Our goal is to step through it, item by item. To do this, we will use Python's built-in iter function to create our iterator. This function instantly returns an iterator object. Hovering over the variable name, you can see we named it staff iterator. A clear and descriptive name. Notice its data type is an iterator, specifically holding string data since our list contains text. Now, the real magic happens when we fetch items using the next function. We pass our staff iterator straight into the next function. Each call advances to the next item. Let's run this to see it in action. First, we get Sarah, followed by James and Olivia. Why? Because the iterator tracking variable remembers its exact position. When you first trigger the next function, it targets the very first item. Then it seamlessly moves forward to fetch James, and finally advances to Olivia. The iterator constantly tracks its state. If we remove one of these lines, notice that we only get 2 outputs. Now, looking at the next code block, notice we aren't passing any index or position parameters. We just call the next function. It paused here. What will the next output be? Predicting Olivia. Let's run it, and there it is. Like magic, Olivia appears. This works because the core job of an iterator is to remember its position. Think of it like a vigilant referee, keeping precise track of where every single runner is standing. When we trigger the next function, it signals the iterator to reveal the next value. What's up next on the list? And boom, there it is. As you can see, the object perfectly supports this next function protocol, seamlessly returning the very next item. But what happens if we keep pushing it and call it again? What do you think occurs? Let's add one more line and find out. Running this triggers a stop iteration error. This might seem like a flaw, but you can actually capture this exception. It is a clear signal that Python has successfully processed every single item. This behavior is completely by design. The stop iteration exception is a built-in notification letting you, the developer, know that the sequence is complete and all items were delivered one by one. Every single element. That final error means mission accomplished. Did you know Python secretly uses iterators behind its for loops? Take a look at the standard for in loop. It iterates through every single item in this list. This list is an iterable object, meaning we can loop right through it. The loop automatically processes each item sequentially. It grabs the item from products and prints it out. But what is actually happening under the hood? Python instantly creates a dedicated iterator object. This iterator wraps itself directly around our iterable, which in this case is our products list. Lists are built-in iterables, so Python sets up an iterator. Now, let us recreate this exact process manually. We can achieve this by using a continuous loop. We will initiate a while true loop. And here is how it behaves. It fetches each item by invoking the next function. We pass the iterator into the next function to capture the element, and then print it out. Now, notice something vital here. Why do we need a try except block? Because when the iterator runs out of items, it triggers a unique signal. That signal is the stop iteration exception. We must catch this exception to safely break out of this otherwise infinite loop. See, to exit a continuous while loop, capturing this error is mandatory, because that is exactly what the iterator throws at the end. Looking closely at how it functions, it requests items sequentially until a limit is reached. It fetches item after item, calling the next function every single time. And the moment the list runs completely empty, boom, it raises an exception. That is the exact error we catch to terminate this endless loop seamlessly. As a result, we get a beautifully formatted, clean output. Laptop, mouse, and keyboard. This output matches our original standard for loop perfectly. And that is the secret magic Python performs under the hood. Let us review the core terminology. First, we have an iterable, which spawns an iterator. Next, you invoke the next function on that iterator to yield each individual item. From there, you can process the data, like printing it out or executing any custom logic. Finally, wrap it all inside a try except block, capture the specific stop iteration error, and cleanly break out of the endless loop. If you loved this deep dive, smash that like button and subscribe for more. Drop a comment below if you have any questions or if something clicked for you today. Hopefully this demystifies Python loops and elevates your understanding of iterables, iterators, and exception handling. See you next time. Did you know Python strings are iterable? That means you can loop through them character by character, just like you would with a standard list or array. Check out this string variable named Google. We are going to create an iterator for it. Since the string is iterable, we can set up a custom iterator to step through it. We do this by calling the next function and passing our iterator, our letter iterator. This is the exact object we pass into the next function. By running this, you can extract one letter at a time from the string, just like you see here with Google. Now you can manipulate or process each character however you like. All because Python strings are completely iterable. Simply apply an iterator to the string to effortlessly loop through every single character. If you didn't know this, smash that like button and subscribe. Follow me as I am on a mission to teach 1 billion people Python. Your support makes a massive difference. Let's keep coding. Dunder methods in Python. Dunder stands for double underscore. You have likely seen these before. They have a very distinct look. Double underscores at the start and end. Take the classic length function, underscores at the beginning and at the end. At both ends, that's why they're called dunder. The D is for double plus under. Dunder. Whenever you see these special double underscore methods, we just call them dunder. Why do they exist? Let's look at an example. Why don't we usually call these methods directly? Let's start with the simplest one, the length function. Imagine we have a list of employees. You can find this length in 2 different ways. First, by invoking the dunder method directly. Running this gives us a count of 3. However, the standard way is using the len function. You pass the employees list into it and get the exact same result. Which one looks cleaner? This or that? Why do we even have both options? Why bother in the first place? Why not just name it length and be done with it? Think of Python like a TV setup. You've likely used a universal remote control, right? If you lose the original remote, you want one device to adjust volume and channels on any television. Python applies this exact same philosophy to simplify. Look here, with a universal interface, you don't need to know the mechanics of how a specific TV handles its volume internally. As long as you press the button, it just works. That is why the built-in len function works on lists, but also on strings. Even though strings have their own underlying Dunder methods, you will almost always use len instead, which automatically triggers that hidden background process. The contract guarantees it's named Dunder len, and we know exactly what the len function delivers. It returns the number of items in a container. That is its core, universal job. This pattern applies everywhere. For instance, with iterators, you call the standard next function. No need to write out those messy double underscores directly in your daily code. You will find this seamless pattern across the Python ecosystem, clean, friendly functions, powered by hidden Dunder methods. View them as that universal remote control. One simple command handles different objects. Whether using len for a list or text, the execution remains flawlessly consistent.